class. Welcome to the last section in chapter 12. Today we're going to talk about conic sections and polar coordinates. Again, I do have a section pretty much just like this in the pre-calculus video series. And I think that I possibly have a couple of examples or more in that section as well. So it might be worth it to check it out if this is not enough for you to gain a proper understanding of conic sections and polar coordinates. The next section, the next chapter we go over, chapter 13, is the last chapter for this course where we talk about um, series and sums and things like that. Okay, it's probably not the funnest, but it'll be okay. This also is probably going to be pretty long a lecture, so don't be afraid to pause if you need to and rewind because we are going to be deriving quite a bit in this section. So I'll try to make sure to take my time and go through it thoroughly for you guys. So let's start off with the theorem. Let F be a fixed point, the focus, and let L be a fixed line, the directrix, in a plane. Okay. So just think about the um, Cartesian coordinate system. That's a plane, right? Let E be a fixed positive number, right? So when it says fixed, it means that these values don't change. Whenever we're going to represent them with F, L, and E, but just think of them as a constant, right? They're a value that is an unknown value that's not changing, right? So yeah, it'll have the letter representations, but it's not a variable, right? But they can take on any value. E in this case has to be positive, okay? F and L, not so much. If the set of all points P that lie in that plane, such that the distance from that point P to the focus divided by the distance from that point P to the directrix is equal to this value E. Okay, so that means that the ratio of values from the point to the focus over the point to the directrix always has the same um, value, right? The ratio of those two values is a constant value, which we call E, right? If that's true, then it's going to be a conic section, okay? And depending on the value we have for E, will determine which kind of conic section we have. Remember, E has to be a fixed positive number, and so we call it the eccentricity. And if the eccentricity is between 0 and 1, not including 0, not including 1, again, fixed positive number, so 0 is not included. In this case, we're not going to include 1 either. It'll be an ellipse, right? So if this ratio between the distances of the point to the focus and the point to the directrix is, let's say, 0.5, it's going to be an ellipse, okay? And so if it's equal to 1, it's going to be a parabola. And so the shape of our conics change depending on the eccentricity, right? Obviously here. And if it's larger than 1, it's going to be a hyperbola, right? And so our value of E determines determines the shape of the hyperbola, right? And the value of E for the ellipse determines basically the roundness of the ellipse, okay? The smaller that E is, the more we're closer to a circle. The larger that E is, the more we're starting to kind of get long and thin, right? Hyperbola as well. The different values, the different ratios that we have here, will change how our hyperbola looks as well. And we can go into that later when we get closer to that in this section. So let's go ahead and do a proof. I don't think we proved too many things in this course. It is a calculus course, but you should start to see some proofs. And if this was a standard textbook that I was using and not a course reader, there would be a lot more proofs, right? So let's go ahead and go through this. So basically what we're going to do is in order to prove this, I have to start with the things that I'm given, right? So what am I given? It's telling me that I have a focus, I have a fixed line, I have a positive number called eccentricity, which is E. Um, and all of those things that I'm given are related by this equation, right? The distance from that any point to the focus that I was given here over the distance from that point to the directrix that I was given as well is always going to equal this E value that we're talking about that I've also been given. Okay. So what we're going to do is we're just going to kind of, given that all of that is true, we're going to prove that the different values of E will determine what kind of shapes that we have here, an ellipse, a parabola, or a hyperbola. Okay. So that's the direction that we're going to be going. So try to bear with me as we kind of flesh that out, right? So F. Okay, so I'm going to restate the things that they told me I have. So I'm going to call F a fixed point, focus, right? And I'm going to say that I have a directrix that I'll call L. And both of these are elements, these are objects that are in R2. Okay, they're in the Cartesian coordinate system. Okay, this is a point in the Cartesian coordinate system. This is a line, a fixed line, horizontal line, or vertical in the Cartesian coordinate system, rectangular coordinates. Okay, so I'm going to make some assumptions here just to make things easy for me. I'm going to say let L be 0 and let this focus be at 0D. So basically saying let the directrix be the x-axis. Um, since it's not specified, it's just generalized. We've actually done this fairly generalized already. Then let the focus be at 0D, so above or below, because it's not specified if it's positive or negative, our directrix. Okay, so here, D is the distance from the focus to the directrix. So if you remember, it changes for everything, but in the parabola example, it was 2p, right? I went up 1p to get to the vertex and one more p to get to the focus. In the hyperbola and the ellipse, we haven't really talked about where the directrix is. It's not necessary for anything that we do. So I'll reference this to the parabola because that'll make more sense for you guys, right? So let this be the directrix and the focus of the Conic section, right? So L equals 0, I'm going to call it the directrix. And at 0D, where D is the distance between the focus and the directrix, that is going to be where my focus lies at this point on the uh, y-axis, right? So I'm going to let P, X, Y be any point on the conic section. Okay, so whether it's an ellipse, parabola, or hyperbola, this is just some point on one of those objects that I have. Okay, the point PXY can be rewritten in polar coordinates as r theta, right? So r theta is the polar coordinate form for my point xy that is in rectangular coordinates, Cartesian coordinates. Okay. So 0D in terms of polar coordinates is going to be at a uh, radius of D. Okay, that's how much I moved out, and pi over 2, because this is at 0D, right? So on the x-axis, I'm sorry, on the y-axis, I just move up the distance of D, so that means it's radius of D, and the angle direction is straight up, so that's pi over 2. So this in polar coordinates is D pi over 2. So then the distance from my generic point, r theta, to the focus, which is again at d pi over 2 in polar coordinates, will look like this. So I'm subtracting the x values, right? So r cosine theta is the x value for p, right? P is x and y, remember? So I subtract the x's. For the focus, it's d times cosine of pi over 2, because that's the direction I'm going. And then same thing for the y values, right? So for my point, y equals r sine theta. And for this, it's going to be d sine pi over 2, right? Because again, it's the y value, so it's r cosine theta, right? So I square both of these and I add them together. So I take the differences, square it, take the difference, square it, add it together, and take the square root, right? So first things first, I gotta expand this. Okay, so both of these are just perfect squares. So this will be r squared cosine squared theta. Okay, um, this we don't have to actually worry about because at pi over 2, cosine is 0. So I just have this first term. Okay, here for sine pi over 2, I actually have 1. So this is r sine theta minus d. So I have r sine theta minus d squared. So then we'll go ahead and square that second half now. okay, here. So this will be r squared sine squared, okay? Then I multiply these two together and double it, 2r d sine theta, negative, right? Because it's negative in the middle. And then I square the last term and add it, so that's d squared. Okay. So the first two are nice because we have r squared in front and cosine squared and sine squared, so I can pull out that r squared and it just turns to 1. So now I have r squared minus dr sine squared plus d squared. Okay. And this is not a perfect square or anything like this. This is not anything that'll allow me to factor it and it'll look nice or anything like that. So we're kind of stuck here, right? The distance from my point to L, the directrix, is just the differences in the y values. So that's just r sine theta. Okay, that's what, especially since this L is at the origin, right? Or I'm sorry, is at the axis, L equals 0. So I'm on the axis, the x-axis. So I just need to know the distance from P all the way down. So P is at xy, right? So the distance straight down from that is y. It went up y. And so y in polar coordinates is r sine theta. Okay. So when I make this ratio, right, I'm going to have my little square root thing I have here on top. And on the bottom, I'm going to have this r sine theta. Okay, because that's the distance from my point to my x-axis, basically, right? It's just the y value. And so we can set this up. So I'm going to rearrange this a little bit. I'm going to have the r sine theta equals this ratio over e. So I'm just kind of manipulating this equation a little bit by multiplying both sides by the distance from P to L and then dividing both sides by e. That's why e is on the bottom here. And then I can just set up that ratio. Okay. So r sine theta is my distance from my point to my focus, okay, over e. And so now we can start to solve. So I multiply both sides times e, and then I square both sides to get rid of this square root. Okay, so that's why I have an e squared, r sine theta squared here. And then now I can start to access these things. Okay, so I'm trying to get this distance. It would be nice to have everything in terms of r. Okay, so let's go ahead and zero this out. And I'm going to change to rectangular coordinates. So I changed into polar coordinates, did some math, and then we're changing back into rectangular coordinates. So r squared is x squared plus y squared. Okay, 2d r sine theta, so that's going to be 2dy, right? D squared is just d squared. That's not part of anything. It's just a constant. Okay, and here I'm gonna have e squared, the eccentricity squared, and this is y, right? So this is gonna be e squared, y squared equals 0. So now I'm gonna move my y squares together, okay? And I'll just put them in front. So I have all my y squares in front, and then my regular y term trailing it. Here, this negative 2dy. Then I have my x squares, and then I have my constant, okay, d squared. So here, if I combine these like terms, I can pull out a factor of y squared. So it tells me exactly how many y squares I have. Okay. And from here, I'm going to get into standard form of a polynomial. So I'm going to divide everything by 1 minus e squared, eccentricity. So y squared is alone. I now have negative 2d over 1 minus e squared. That's all the constant, right? Y is the variable here. X is the variable. So it's being divided by 1 minus e squared. And then now I have a constant here as well. So if you notice, I have my two y's in front. Really, what I'm trying to get myself ready to do is to complete the square here. Okay, so I can have a more condensed form. So I'm going to add and subtract a new value of c so that I can factor everything. So in order to complete the square, remember that's negative b over 2a squared. Here, my a is 1 because I divided everything already. So I just need to throw my b over 2, right? So this is already negative, so it'll turn into 2d over 1 minus e squared over 2. Okay. Now when I simplify this, basically this 2 gets to come to the bottom as a multiplier here. So then the 2's cancel. And I have d over 1 minus e squared. And squaring the whole thing gives me d squared on top. And this 1 minus e squared being squared. Now I could expand this denominator, but that's not really going to do anything for me. I'm not going to be able to combine it with anything. So it's better just to keep it compact and factored. Okay. So I'm going to add this and subtract it away. Okay. And when I do that, it's going to make these first 2 terms along with this term um, perfectly or factored into perfect square. And so that inside term is basically what we had here before we squared it when we simplified it. Okay, that's what always how it works. So it'll be the d over 1 minus e squared is the perfect square term. Okay, so 1 minus that value squared, my x squared is still the same. And this d squared over 1 minus e squared, this constant is still there. And then I am subtracting out this value, right? I added it with these 3 so that I can factor it perfectly, but then I have to subtract it away again because I'm not changing the equation. If I just added it, it would no longer be 0, right? Or you can add it to both sides and make it balanced, but either way, I still need to subtract it back over to 0 out the equation. So now my constants look like this, right? They have a very, very common denominator. Looking denominator is not the same yet. The numerators are identical. Okay, so I'm going to go ahead and combine this. So now I have some shift in y being squared, some x squared over something, plus a constant term, right? So I'm working my way into making this look like a conic section, right? A parabola, an ellipse, whatever, okay? So in order to combine these, I need to multiply this top and bottom by 1 minus e squared, okay? So common denominator is 1 minus e squared squared. The d squared from this term is being left alone, but this one needed top and bottom, one more, 1 minus e squared. So what I'm going to do here is I'm going to factor out this d squared, right? So I have this 1 minus e squared minus 1 if I factor out the d squared. And what I'm left with when I do that is d squared, e squared on top, and a negative sign. Okay. Another way to think about this is if I multiply this in, this d squared, I have a minus d squared here for this positive one that cancels. And so what's left over in the middle is just this negative d squared e squared, which is why this is negative, and that's all that's left here. Okay. I could factor out the d squared, and then I would have 1 minus e squared minus 1, and then I would still have a negative d squared in that. Okay. So it's nice here because this is a perfect square. Okay. What I'm going to do now is I am going to move this to the other side. So I'm going to add this to both sides, right? And then I'm going to divide this, I'm going to multiply this by its reciprocal, everything, so that this turns into 1. Okay. So that means I multiply this side times this denominator on top, this numerator on bottom. So that means here I do the same thing. I'm going to have this on bottom, this on top, and one of them will cancel out, so I only have one left. This numerator here will be on the bottom. Okay, same thing here. This numerator will be on the bottom, and in the numerator, I will be multiplying by this. I'm multiplying everything by the reciprocal of this function. Okay, so I have the square term on top, and then this thing squared, this term and this squared, and now this is 1. Now I can start to separate these to look and see what are my A values and my B values. Okay, so remember E and D are constants. So I'm going to say H is D over 1 minus E squared, right? Because I have Y minus some shift. So this is some sort of a translation going on. So let's just call it me moving up or down by H units. Okay. I'm going to say that A squared is this D squared E squared 1 minus E squared squared. All right, so what I'm doing, which you might not be seeing, is I'm looking at this in terms of this as a numerator and this a denominator. So what does that mean? That means that it's the same thing as this over d squared e squared over this term, okay? And so I'm going to call that A. For B, I'm going to call d squared over 1 minus e squared, right? So that's coming from this term right here. Right? So if you were to rewrite this as x squared divided by something so that it's all equal, it would look like x squared divided by d squared e squared divided by 1 minus e squared, right, as the denominator, right? So all I'm doing is I'm flipping that around, okay? So I have I have a squared, I have b squared, okay? And so then that changes my formula to look like the following. X squared over b squared, y minus h squared over a squared equals 1 when e is between 0 and 1. So this looks like an ellipse, okay? And so notice that this is saying that e is a fractional amount. That makes sense for a squared to be the longer one because I have a small amount that I'm dividing by, and the smaller the amount I'm using to divide, the larger I get. And so since this is, let's say this is 1/2, right? This would be 1 minus 1/4. So this would be, 3/4 times 3/4, which is smaller than 3/4, versus this as the denominator, which is just 3/4. Okay. So, um, so this one is actually the larger value here when we're between 0 and 1. Now, if we had a different value of e, then that would change which one is larger and bigger, right? So for here, we have c squared is a squared minus b squared. Again, this is positive, right? So it's the form of an ellipse. So our relationship here is c squared is equal to a squared minus b squared. We can go ahead and test that out. Actually, we will. We're going to find c because if you notice, we don't have an equation for c. So let's go ahead and say that we have a squared minus b squared. So I'm going to take this form and well, I already have it. Okay. And in order to subtract this, I need to make a common denominator again. So I multiply top and bottom by 1 minus e squared, right? So I'm going to get this d squared e squared with one of them, and the denominator is now combined. And I'll do the same thing that I did before. I can pull out this common e term, or I can multiply this across here and see that it cancels out, and then just write what we have left. Right? So for this one, I'm actually going to factor it out. And so I have 1 here minus the 1 here, and then this negative gets distributed, so that's e squared. So those cancel, and I'm left with d squared times e squared times e squared. Okay, so whichever way you decide to do it, whether you decide not to factor out and just distribute this across here, and then subtract everything, you should come out with the same value because that's what the value is. Squared e to the fourth divided by 1 minus e squared squared. And that is our value for c squared. Oops. Okay. So if I solve for c, I just square root everything and I get d e squared over 1 minus e squared. So now I know where my foci are. I was able to derive the standard form of an ellipse in this case. Okay. Um, so if we take c over a, okay, c is the e squared, 1 minus e squared, okay, and then a is square root of that, right? So just de, and then the 1 minus e squared here. Everything will cancel out except for 1e. Okay, so the ratio of c over a is that uh, is our eccentricity, e. So if e is between 1 and infinity, hyperbola, then this is going to be negative, right? Because my e is going to be larger than 1, so I'm going to have 1 minus something positive. And our equation then is going to change to x squared over a squared, so the larger value will be on the x side here. And we will have a subtraction, right? And again, to find the c squared, it would now be a squared plus b squared because the b squared would now be changing values, right? Because remember the a squared term was it was squared, right? It's 1 minus e squared squared. So even if this was negative, it ends up getting squared and becoming positive. The b squared is 1 minus e squared, so it'll just be negative. So all the things that were associated with it are now negative. So on the b side, we now have a negative sign. Remember, it was a squared minus b squared, so now this changes signs to being positive, right? So c squared is a squared plus b squared in this case. And um, there we go, right? So the only case that we have left that we didn't talk about was when it's equal to 1. And when it's equal to 1, we know that those two values are equal already. We've done that quite a bit, okay, right? This parabola part. So we're able to show the starting from the parabola portion and then kind of working our way down to the ellipse and the hyperbola, okay? So let's talk about this now in polar coordinates. So we started to bring eccentricity into it, right? But how does this look for our polar coordinates, right? So polar coordinates, conic sections are a lot easier to deal with. Um, they're a lot easier to deal with, okay? I'm sure you're already used to dealing with ellipses and stuff like that from like implicit differentiation where a lot of people have you differentiate an ellipse. And that's probably most people's exposure to them. For us, since we're dealing with angles and polar coordinates, it's very easy to rotate things, right? And since there's so much symmetry in a circle and ellipse and hyperbolas and all this kind of stuff, it's easier to deal with them in polar coordinates because we're allowed to rotate stuff, okay? So let's consider a parabola. So we had kind of worked out all this stuff, right? We're assuming that y is equal to L. This distance is y minus L. Let's say that we say that this is 2p, so then just the vertices, the vertex is distance of p, okay? And so we know that the distance from the point and the focus and the distance from the point and the directrix is equal, okay? And so that their ratio between each other, since they're equal, which is equal to E, is equal to 1, right? Uh, that's the easiest way to look at this, right? So we just went through a small proof here about every point that satisfies this, or E being a constant, is some sort of a conic section, right? So for a parabola, if those things are equal, the eccentricity is equal to 1, right? That's the parabola case. So let's look at the triangle that's created here, this right triangle, okay, right here. And we'll use these values to help us look at this parabola in terms of polar coordinates. So from the line from F to P, we'll call that a radius of r and an angle of theta, right? So we know that the x distance is r cosine theta and the up distance is r sine theta. Um, we know that this distance here is 2p above L, right? So we have 2p and then whatever this is, um, 2p plus r sine theta is this y minus L, right? So note that we're calling the distance from P to F R, our radius, okay? And the distance from P to L, right, is this r sine theta plus the 2p more, okay? Our 2p plus this r sine theta. So our ratio, that equals E, which in our case equals 1 for a parabola, can be manipulated so that it looks like R for the distance from P to F, and the distance from P to L, okay, is r sine theta plus 2p. And that's going to equal my eccentricity, uh, which is 1 in this case. But here, we're going to keep working so that we can find this polar form. So remember, for the polar form, we want r to be isolated. Okay, so we need to move some stuff around. Okay, we know that E is 1, but we're going to just kind of work with it here. Keep it generalized and see if that tells us some stuff about the other type of conics in polar coordinates. So I'm going to multiply both sides by this denominator. Okay, I'm going to distribute this E across and then subtract this r sine theta so that I have all of the r's on one side. I can now pull out the common term of r. So I have r times 1 minus E sine theta. Okay, and that's going to equal to 2pe. Divide both sides so that I have r isolated, and then that is the form of a parabola. Okay, here E being 1. Okay, So R equals dE over 1 minus E sine theta is the equation of a parabola as a polar equation when the eccentricity is 1. So if we change the sign on sine theta, then the term, um, the graph flips across the polar axis. Okay. So if we make this, instead of 1 minus, I make this 1 plus, it's going to flip across. So in this parabola, let's say it's focusing up, it's going to flip downwards, right? So if I make this 1 plus E sine, the it flips across the x-axis, right? The polar axis. If I change the sign to a cosine, instead of it being orientated up and down as sines do, it would start to be orientated from left to right. And if I start to change the signs with that, I can also flip if it's pointing to the left or pointing to the right. Okay. So this would be ED. So this y equals L is the directrix. And so this would be the general form here. Okay. If I change the sign to plus, well, now it's going to be concave down instead of concave up. Right. If I use cosine instead, it will point in this direction. And if I use the opposite sign of cosine, it will point in this direction. So changing the signs in front or changing sine to cosine will change the orientation of our conic section. Okay. So this leads us to another theorem. So a conic is represented as a polar equation if it has the form R equals ED divided by 1 plus or minus E cosine theta, or R equals ED divided by 1 plus or minus E sine theta. And the different values for the eccentricity will tell us if it looks like a parabola in this orientation, an ellipse with one of these orientations, or a hyperbola with one of these orientations. Again, it's the eccentricity that determines which kind of conic section, but they can all be manipulated and flipped around in this same fashion that we have shown for the parabola. Okay, again, it's the eccentricity which tells us the type of conic. Okay, so whether cosine or sine tells us am I going along x-axis or along the pi over 2 axis, the y-axis, or the different values of positive and negative will flip me around those axes as well. Okay, very important to try to remember. So let's go ahead and do an example. Okay. So consider the polar equation. R equals 5 over 2 plus 3 sine theta. So this is going to be some sort of a conic, right? I'm not sure exactly what, because I don't know what the eccentricity is, because the eccentricity is always mixed in with the value of d, the distance from the directrix to the focus. Okay. What I need is I need it to be in one of these standard forms, either cosine or sine, plus or minus, doesn't really matter. But I need it 1 plus or minus some multiple of cosine and some number on top. Okay, but I need the 1 there. I don't have a 1, I have a 2. So what I'm going to do is I'm going to divide everything by 2 so that it looks like what I need it to look like. Okay, so I want to put it in the standard form because it's a plus and a sign. So I will divide everything by 2. Okay, so I have 5 halves. Divide this by 2, divide this by 2. So everything has been manipulated equally. Now it's very easy because it's my standard form. Okay, E times D is 5 halves, and E times sine theta is 3 halves times sine theta. That means that E is 3 halves, which means that 3 halves times some value, the distance to my focus, is 5 over 2. So it's very clear that E is 3 halves, which is larger than 1. So my eccentricity is larger than 1. That means that this is a hyperbola. Okay. E times D is 5 halves, and I know E is 3 halves. So solving for D, I have D is 5 thirds, right? Uh, Multiplied by the reciprocal here. So since this is a graph of sine, okay, I know it's going to be orientated top and bottom, and in fact, it's a positive sign, so it should actually be pointing down. It's a hyperbola, so it has a top and a bottom, so it doesn't really matter which one is down or up because of the symmetry there. But I know the orientation is top to bottom, okay, because it's a sine. So the transverse axis then is along my y-axis, or along that line pi over 2. Okay. So we want to find the vertices. We need to evaluate then at pi over 2 since I know that's the orientation. So I can find my vertices by plugging pi over 2 um, into my r function. Okay. And then I can do the 270 degrees, which is 3 pi over 2 as well. So 90 degrees and 270, so the two ends of the poles, so along the pi over 2 line. And so for pi over 2, when I plug this in, I know sine of pi over 2 is 1. So I get 5 over 5 basically. Okay. And then, so the first vertices is at 1 pi over 2. Okay, so that's the radius. So this is in polar coordinates, right? This is the um, radius and the angle. So y-axis, that makes sense. For the second point, I'm going to use 3 pi over 2. And so 3 pi over 2 over sine is a negative 1. Okay. So 5 over 2 minus 3. So this is so 2 minus, right? Because sine 3 pi over 2 is negative 1. So I have just a 5 and it's negative. So radius of negative 5 at 3 pi over 2, which I can rewrite then as just 5 at pi over 2. Okay. So if I change the direction of the radius, I got to change the angle as well. So my hyperbola is centered at 3 pi over 2 because 3 pi over 2 is right between 1 pi over 2 and 5 pi over 2, right? So the center is along pi over 2, but between those, directly in between those two vertices. Okay, so that's where the center of this is at. The foci can be found with this E divided by C over A. I know what E is, and I know what A is. Okay, I know the distance to the end of the center, right? It's a major axis, goes from 1 to 5, so it has a length of 4. So half of that is 2. So I know my E up here, was it 3 halves? Okay, my A is 2, and that gives me my relationship here, right? So A is half of the distance between the vertices along the pi over 2, which is 4, right? And half of that is 2, as I stated. So C is 2 for A times the eccentricity, 3 halves. So C is 3. Okay. So then from the center up, 3 is how I find one foci, and from the center down 3 is how I find the other foci. So I have 3 plus 3 pi over 2, which is 6 pi over 2. And then I can go down 3. So 3 minus 3 on the pi over 2 line is at 0 pi over 2. So at the origin. And for a hyperbola, I know c squared is a squared plus b squared because I don't know anything about b, right? But I do have c and a. And so solve for b squared, right, is going to be c squared minus a squared. C squared is 9. A squared is 4. So um, b squared is 5. So b is root 5. And now I have all the information I need. I know A, I know B, so I know my asymptotic lines, I know my foci, my vertices, I know the center box information, everything, right? So the first one is at a radius of 1, okay? 1 and pi over 2 is the first vertices, 5 pi over 2 is the second, right? So 1, 2, 3, 4, 5. And then for my foci, it's at 6 and 0. So at the origin, and at 6. And so if I put this over rectangular coordinates, it would look the same. Okay, so that's how we do that. All right, and that is our conic sections in polar coordinates. See you guys for chapter 13.